One of my favorite topics in chemistry is learning about the energetics that occurs when bonds are formed. And so we're going to talk a little bit about that in this video. Our learning goals is to understand potential energy diagrams for bond formation. This gives us some insight into how these atoms interact as they're forming a bond. So let's ask this fundamental question: why do covalent bonds form? All right, so let's suppose we have one atom, and I'm not going to specify what atom it is, but it's got a charge on its nucleus of plus QA, and there's another atom which has a charge of plus QB. Now, in this case, the red dots are indicating electrons that are in the outermost shell or valence shell, and the black circles are vacancies in that shell on each of these atoms. So in other words, there is a possibility of moving together and filling in to form a covalent bond by sharing electrons. So the gray areas around each of these nuclei are core electrons. So they are partially shielding these nuclei, which means that the positive charge isn't going to be the full amount. It's going to be less than the amount that would normally be on that bare nucleus. But it's nevertheless still a positive charge that is felt by electrons outside the atom. Now, as these things move together, this shielding by the core electrons is going to mitigate that positive charge, but it's not going to eliminate it altogether. So the electrons on one atom are still going to feel a little bit of that positive attraction toward the other nucleus. What this means then is that as these atoms get close together, the electrons on one can move in to fill, in essence, a vacancy in the electrons on the other. This leads to the sharing of these two electrons, and that is what forms the bond. Now, this is a very simplistic picture of how a covalent bond forms, but it gives you an idea and hopefully helps you build some intuition about what are the forces responsible. These are basically electrostatic forces that are bringing these things together. And a lot of times we use the analogy of falling in love is like forming a covalent bond. So you can imagine the attraction between these atoms is irresistible, so that they form a bond and share their lives together after forming that bond. Let's look at this in terms of the energies that are associated with this process. Now, we're going to look at the forces between particles that create a force field. That is the electrostatic forces. So this attraction creates a force field. Energy then is required to move the particles within this field. All right, so if the field is attractive, it's going to reduce energy, and if it's repulsive, then it's going to increase energy. Let's look at an example of pulling two magnets apart. Okay, it requires a lot of energy to pull them apart, but it doesn't require much energy. In fact, you gain energy, you lose energy, I guess you will, by pulling them together. Now, for attractive forces, the closer objects are, the more energy it takes to separate them. Okay, I want you to think about that. Two atoms are coming together, they're attracted to each other. As they get closer, it's going to require more energy to pull them apart. Okay, since you're adding energy to pull them apart, as they come together, the energy is actually getting smaller, it's going negative. So we're going to define energy in this case to be zero when the particles are an infinite distance apart. And that means as they come together and they're attracted to one another, the energy has to go down because we will have to add energy again to pull them apart again. So what does this look like? Okay, so I'm going to draw a little bit of a graph here where I'm going to use energy on the vertical axis, and on the horizontal axis it's going to be the distance d between two atoms A and B that are going to form a covalent bond. Now I'm going to make some little diagrams to sort of illustrate what that distance looks like. So here's a case where the atoms are very far apart and there's a little bit of an attractive force, so they're slightly below that 0 point. As they move closer together, what happens to the energy is that it goes down. But when we get to the bottom, to the lower left part of that curve, it requires more energy to get back to 0, to separate those atoms again. That's why it's going negative. As we get them closer together, you can see that the curve continues to go down. So as we're bringing atoms together, they're getting more strongly attracted to one another, and it requires more energy to separate them. As they go further down, they will reach a point at which you can no longer go further down because the electrons on each atom are beginning to have repulsive interactions with each other. They're beginning to push each other apart. When the repulsion between those electrons and the attraction of electrons for the other nucleus are roughly equal, we say that the atoms reach an equilibrium. That is, the forces on them don't push the atoms further apart, don't pull them closer together. So this is really the minimum in energy that we can get when we pull these atoms together. As we continue to push atoms together, however, we're going to see the energy go up again. Now we're putting them into an uncomfortable zone. And you can think of this as if you meet a friend on the street. You might cross the street, you might shake hands with them, but if they get too close to you, if they get like in your space, you get very uncomfortable. Your energy goes up. All right, and for atoms that can continue on until they're, in fact, the energy is above the 0 point. This is a really repulsive region where the atoms are so close together that they can hardly stand it anymore, and it forces them to move apart. So this is essentially what the potential energy curve looks like when two atoms are coming together to form a bond. And there are several things that we can get from this diagram that tell us something about the bond that is formed. First of all, the bottom of that curve tells us about the energy of the bond. The amount of energy it takes to go from the bottom of that curve up to the 0 point, where the same as the energy of the atom separated, is the energy of the bond. So now we have a concept of how much energy it takes to break a bond. And it always is energy that has to be added to the bond to make it break. We can also see that the location of that basically describes the equilibrium bond length. Well, that is the bond length of that bond that's formed. That's where those atoms like to be when they form that bond, that distance apart. Now, how would we compare two different potential energy diagrams for different bonds? So here's one like the bond we just formed between A and B. And let's suppose we have another pair of atoms, X and Y, and their curve looks something like this. Now, first of all, I can tell you could infer from this that one or both of the atoms X and Y are larger than the atoms A and B. Okay, why is this? Because their equilibrium bond length is longer. So the atoms are larger, they can't get as close together, they form a longer bond. All right, we might also infer from this that the energies, which is the distance between the bottom of those curves and the horizontal axis, the energies are also given by this, and the energy of the XY bond would be less than the energy of the AB bond. All right, we're already beginning to see now a correlation between longer bond means weaker bond, or shorter bond means stronger bond. This is a general correlation that we'll see in a number of different cases, but this is a great illustration of how that works. So I hope you can keep these curves in mind when you think about bond formation, because these tell you an awful lot of information about both the length of the bond and the energy of the bond when you can make them.